In standard software engineering benchmarks, today's large language models are now routinely synthesizing functional, complex code structures completely autonomously. But when we attempt to measure those same models' cybersecurity capabilities, the evaluation methods rely heavily on capture the flag, or CTF environments. CTFs are synthetic, isolated logic puzzles. They test specific vulnerabilities in idealized conditions, which completely fails to simulate the immense chaos and the deep interconnectedness of a massive real-world production codebase. To accurately gauge AI in a security context, we require a dynamic evaluation framework built entirely from historical, real-world vulnerabilities. Measuring true offensive and defensive AI capabilities demands deep repository-wide reasoning, not isolated, localized code edits. This requirement is met by CyberGym, a massive cybersecurity benchmark developed by researchers at UC Berkeley. The scale here is vast. The benchmark isolates 1,507 real-world C and C++ vulnerabilities distributed across 188 widely used software projects. These vulnerabilities are extracted directly from the lifecycle of Google's OSS Fuzz, a continuous automated testing service that bombards software with random inputs to find crashes. The agent's primary task within CyberGym is highly specific. Given a text description of a vulnerability and the raw codebase, it must generate a proof-of-concept exploit, or POC, to actively trigger it. Despite their proven coding prowess, state-of-the-art models max out at a roughly 22% success rate on this task. These low success rates demonstrate that reproduction remains difficult for current agents. Understanding why requires a deep investigation into how the benchmark is actually constructed. A target project monitored by OSS Fuzz goes through a daily automated update cycle. Researchers binary search the commit history to pinpoint the exact patch commit fixing the vulnerability. From this point, they extract two artifacts, the flawed pre-patch codebase and the fixed post-patch codebase. Finally, they extract the original fuzzer-generated proof of concept, the mathematical ground truth the flaw exists. Finally, they extract the vulnerability description. To standardize this, an LLM rephrases the original commit message, removing direct hints while keeping technical details intact. Extracting these four specific artifacts transforms a chaotic historical fuzzing event into a pristine, isolated sandbox for AI evaluation. Relying on an AI to judge another AI's security exploits introduces significant bias and error. A benchmark of this scale requires a purely execution-based metric. The researchers use compiler sanitizers, specifically address sanitizer, or UBSAN, as the absolute ground truth oracle. These tools monitor memory operations and intentionally crash the program with an error report if a flaw is triggered. The AI agent generates a script containing its payload, which targets two containerized executables. First, it must trigger a sanitizer crash within the pre-patch executable. Second, the exact same POC must execute without any crashes on the post-patch executable. This dual validation proves the agent targeted the specific memory safety flaw addressed by developers, rather than accidentally tripping a random, unrelated bug. This deterministic, execution-based oracle makes CyberGym a scientifically rigorous proving ground, establishing a ceiling that most current language models cannot breach. This vertical bar chart compares the success rates of various AI models on the CyberGym benchmark. Starting with specialized software engineering models like SWGym 32B, the success rate is nearly flat, hovering between 0.1% and 2.0%. Their failure rate suggests that standard coding ability does not translate directly to exploitation ability. Open-weight models like Qwen and DeepSeek show a marginal increase, landing between 4 and 9%. Performance jumps with general-purpose frontier models. Claude Sonnet 4 reaches a 17.9% success rate. The benchmark ceiling is 22.0%, reached by GPT-5 using its maximum reasoning effort. There is very low overlap in the specific tasks successfully completed by these different models. This implies they possess highly distinct capabilities, rather than a unified, optimal approach to finding vulnerabilities. This line graph reveals the primary variable dictating success rate on the y-axis against the POC byte length on the x-axis. For extremely short payloads, under 10 bytes, models achieve over 43% success. This collapses to roughly 10% for payloads exceeding 100 bytes. language models easily synthesize simple format strings. They fail at constructing complex, multi-layered binary file formats. The empirical data proves that generating long, mathematically precise inputs for security exploits requires different reasoning mechanics than standard software engineering. Agents frequently trap themselves in a context window exhaustion loop. Instead of writing and executing an efficient terminal script, they attempt to print thousands of payload characters in raw plaintext, overwhelming their own memory. Another failure mode is the retrieval loop. Agents burn their entire iteration budget executing repetitive search commands like grep and find without extracting any semantic meaning from the codebase they are scanning. Finally, agents suffer from premature termination. Lacking critical self-evaluation, they declare success before actually confirming the sanitizer crash with the benchmark oracle. These behavioral loops highlight a systemic lack of deep repository comprehension. This is the primary barrier preventing current agents from reliably navigating complex vulnerability reproduction. Recall the rigorous success criteria established earlier. A valid POC must crash the pre-patch version, but run cleanly on the post-patch version. During evaluation, researchers discovered a critical anomaly. Agents generated POCs that successfully crashed both the pre-patch and post-patch executables. This implies the historical patch was incomplete, leaving the software exposed. Or, the agent inadvertently synthesized an exploit triggering a previously unknown flaw. This demonstrates how the benchmark's execution-based design allows language models to operate as functional vulnerability scanners. In a final experiment, the researchers removed the vulnerability descriptions entirely. They deployed the agents for open-ended discovery across 431 live, modern open-source projects. By utilizing GPT-5 with maximum reasoning effort in this exploratory setting, the agent functioned much like an automated fuzzing engine. This open-ended deployment yielded 34 confirmed, previously unknown zero-day vulnerabilities in production software. These 0 days consist of high-severity memory safety issues, including out-of-bounds reads and null-pointer dereferences. Following responsible disclosure protocols, the Berkeley researchers ensured the affected projects were notified and patched before public release. While autonomous AI hackers remain bottlenecked by deep repository logic in static benchmarks, their integration into continuous evaluation pipelines is already yielding immediate, practical security impacts today.